Let's understand work in physics in this video. Have you ever carried a bag and said you are doing work but not moved it up or down? In physics, work means a force causes a displacement of the point where it acts in the direction of the force. So, if a force acts but the object does not move, the work done is zero. Let us learn the main formula for a constant force, step by step. If a constant force F displaces a body through distance d, the work done W equals F times d times cosine theta, where theta is the angle between force and displacement. Only the component of the force along the direction of motion does the work, and the perpendicular component does zero work. The unit of work in the SI system is the joule, also called Newton meter. Work can be positive, zero, or negative. So let us see simple examples for each case. When force and displacement are in the same direction, theta is 0 degrees, cosine 0 degrees is plus 1, so work is positive. For example, gravity doing positive work on a falling body. When force and displacement are at right angles, theta is 90 degrees, cosine 90 degrees is 0, so the work done is 0. For example, centripetal force for circular motion. When force opposes displacement, theta is 180 degrees, cosine 180 degrees is minus 1, so work is negative. For example, friction opposing motion. Now let us solve some questions to make this clear. We will work through each step. Question number 1 asks a block of mass 2 kilograms is pulled by a force 40 newtons upwards through height 2 meters. Find work done by the applied force and by its weight, G equals 10 meters per second squared. Step 1. Compute work done by the applied force. Angle between force and displacement is 0 degrees, so cosine 0 degrees is 1. Thus, W applied equals 40 times 2 times 1, which is 80 joules. Step 2. Compute weight. Weight magnitude equals mass times G equals 2 times 10, which is 20 newtons. Downward. The displacement is upward, so angle between weight and displacement is 180 degrees. Cosine 180 degrees is minus 1. So W, weight, equals 20 times 2 times minus 1, which is minus 40 joules. Next example. A constant force F equals 4I plus 3J acts while a particle moves from point 12 to point 45. Find the work done. Compute displacement vector. From 12 to 45 gives 3I plus 3J. Then work equals dot product of force and displacement, which is 4 times 3 plus 3 times 3, giving 12 plus 9 equals 21 joules. Another example uses a perfect differential. The small work dw equals y dx plus x dy, which equals the differential of xy. Integrate from 0.23 to 56. Compute xy at limits. At start, 2 times 3 equals 6. At end, 5 times 6 equals 30. Difference is 24 joules. For a variable force along x, we write small work dw equals f of x times dx. And integrate from x1 to x2, the area under the force versus x graph also gives the work. For example, if force equals 0.5x plus 10 newtons and displacement goes from x equals 0 to x equals 2 meters, integrate 0.5x plus 10 with respect to x. Primitive is 0.25x squared plus 10x. Evaluate 2 gives 0.25 times 4 plus 20 equals 1 plus 20 equals 21 joules. Brief note on conservative forces. A force is conservative if work depends only on initial and final positions and not on the path. Gravity and ideal spring forces are conservative. Work done by a conservative force in a closed path is zero, and we can define potential energy for such forces. Work energy theorem says net work by all forces equals change in kinetic energy. That is, net work equals 1/2 mv final squared minus 1/2 mv initial squared. As a quick example, A body dropped from height h reaches ground with speed v, given by v equals square root of 2gh, found by equating loss of potential energy to gain in kinetic energy. So, what do we learn from this? We learn that work measures force times displacement. Along the force, sign shows help or opposition. And we can compute work by dot product, by integration, or from area under an fx graph. Let us quickly remember constant force formula W equals Fd cosine theta. Only parallel component contributes, unit is joule, and net work changes kinetic energy. Keep practicing the examples, do not worry about mistakes, and explore more work problems on EduRev to build confidence and speed. Thank you for learning today. Keep solving and enjoy physics on EduRev.